So far in A-level maths, we will have looked at a few different types of integration as methods for finding the areas bound beneath curves and the axis and any other lines the question may throw at you. This can be just regular integration or integration by parts, integration by substitution. What if, though, we're just content to estimate the area underneath the curve rather than getting exactly the right value? Or what if we weren't sure what kind of integration to do, so instead we do perhaps a slightly older method of just trying to split the shape up into smaller, more manageable shapes. For instance, if we had a curve such as this, which is then tending off, or a curve like this, which is then rising exponentially, what we could do is draw some vertical lines that split this area up into more manageable chunks. Same here. Ideally, the width between these lines being the same in each case. If we were to then join up the corners of these lines, like so, what you would end up with is a set of trapeziums. And because of this, we're now going to call this method here the trapezium rule, splitting up the areas into curves into trapeziums for which we can work out the areas individually and add them up together. Just as a recap, in case we're not sure, for trapezium, which is where you have two parallel sides and then some other diagonals between them, the area is half of A plus B, where A and B are what we're calling these parallel sides, and then times the distance between them, times the height. Okay, so that would be this here. Now, in the cases of these diagrams here, your parallel sides are these vertical lines here. They're parallel to each other, and the height is actually the distance between each of the vertical lines. So what we can do is if we were to just start like labeling points, so this on the x-axis would just be 0. And then what I'm going to do, just to help it make it clear that it's for the area of trapezium formula, this x value here, we're going to go h along. The next, therefore, will be 2h, 3h, and 4h, because again, they should have equal widths between the strips. They should each have a quote-unquote height of h. Same goes on this diagram here. And then in the y-axis, we'll say so here this first y coordinate will be y0, and then you've got y1, y2, y3, and y4. These obviously bunching together as these y coordinates here, these heights get close and close together, the curve tending off. Meanwhile here, if we say the first one is y0, then y1, y2, y3, and then rising up y4 approximately. This is just for demonstration purposes. To then get the areas of each of these trapeziums, we'll apply them into this formula one at a time. Let's look at the left-handmost one. So we're going to have a half. Now the A and the B, the parallel sides for this first one, is going to be y0 for the first height, and then y1 for the second. And this will be times that distance of h. For the second one, that would then become y1 plus y2, because this trapezium here, the y1 is still one of its parallel sides. It's just now that's the shorter one compared to a longer one of y2. And once again, the difference between here is h again. So then you do the third one over half, now y2 plus y3, because again now y2 is once again shared, but now is the shorter side, times h, and so forth and so forth. There'd be a simpler way of doing this though, more in one go. Because every term is being times by the same half and the same h, we could bring this out in front, so it's just like h over 2. Now you may then see this next bit printed using curly brackets. You can use it if you want, or just regular ones. It's just stylistics, and it helps you differentiate later because we are going to end up with a bracket inside this bracket. this then, you end up with one lot of your y0. Now add to that, because we're going to be adding together all of these areas, obviously, to get the overall area underneath the curve, you'd end up adding your last y value. So you'll just say n here for however many y values you had. Onto this, though, you'll then have two lots of every other y value. So y1 appears twice, y2 appears twice, 3 would, and so forth, if you keep on adding them up. So it's then, so y1, add y2, all the way up to yn minus 1, whatever that ended up being. Once you have this, you just plug the values into a calculator all in one go, and this will get you an approximation for the area. The reason why this is only an approximation is because, as you can see here, this trapezium is not fully filling this area. You've got this bit here, which is not being accounted for. Same here, here, and here. Therefore, if the curve is tending off, if it's becoming a horizontal, your trapeziums are going to give you an underestimate for the area. The best that you can do is to actually have more trapeziums to make H narrower, to get more strips, because the more strips you have, the more in line with the gradient of the actual curve each individual slant here is going to be. But again, you're always going to end up with this tiny pocket there that's not being accounted for. Meanwhile, if the curve instead is curving upwards, exponential, you end up with this space underneath the lines. Here, obviously mine isn't a perfect drawing, but there's going to be some kind of space between the straight line and a curve, because inherently a straight line and a curve cannot perfectly match up with each other. This means that if the curve is bending upwards, your trapezium rule is going to give you an overestimate. And once again, the solution to this would be to have just more trapeziums, because then each slanting line is going to be closer to the actual gradient, even if it's not exactly the same. So let's just say, for an example, we were to work with this here. So find an estimate of, so the definite integral between 4 and 1 of 16 over x squared minus x over 2 plus 1 dx using 6 strips, and the strips would be of equal width. So, because we're going between 1 and 4, that's a difference of 3. If you've got to cover 3 in a total of 6 sections, well, that would be going up in halves, right? So you'd have 1, 1.5, 2, 2.5, 3, 3.5, and then finally 4. To be clear, you probably will have a table given to you in a question. It's a kind of a just in case. If they don't give you a table already set out, this is how you work that out. So what's the difference between the bounds? Divide that by the number of strips. That tells you what interval you're going to go up in. 3 divided by 6 is a half. At this stage then, you'll literally just take these x values, plug them into this equation in your calculator, and work out each value individually. So if you were to do that with this one, so 16 over 1 squared minus 1 over 2, add 1, that would give you 16.5. Doing it again with all of them, you end up filling out your table with 7.361 for 2.31, 1.278, 0.556, and then lastly 0. Now that we have these y values, we can plug them into the trapezium rule formula. How h is going to be a half, because that's the interval we're going up in, so 0.5 over 2, and then within our curly brackets, the first y is 16.5, and then technically the last one is plus 0, and you'll add on to that 2 lots of everything else, so 7.361 plus 4 plus 2.31 plus 1.278 plus 1.556. To be clear, when I did write these down, in some cases they were recurring decimals, so I did just round them in this table. Ideally, in your calculator, you will try to keep as precise a value as possible. And either way, this should get you an approximate area of 11.877. We don't have any units for this, so just like units squared if you insist, or just the main thing is you have the number. If we can see what we've done here, let's just see how you could get along with a question of your own. So the finite region R is bound by the curve y equals x over 1 plus root x, the line x equals 1, the x-axis, and the line x equals 3. Using the trapezium rule and 4 strips of equal width, estimate the area of R, and then, therefore, estimate the value for the integral between 3 and 1 of 5x over 1 plus the square root of x dx, in each case giving your answer to 3 decimal places. And so with the trapezium rule, the main thing is just identifying what numbers you need to plug into this formula here. Look back at the example we just did, if needs be. Pause the video, have a go for yourself, and then press play again when you're ready to compare. So, what we're going to need to do first of all is work out what our y values are going to be. So, because we're going between x is 1 and x is 3, and we're going to be doing 4 strips, we're going to be having, so x is 1. We're again going to be going up in halves, so 1.5, 2, 2.5, and 3. Yeah, just if we hadn't noticed before, you end up with one more x value than you do the strips, because you have, so it's the strip between 1 and 1.5, the strip between 1.5 and 2, between 2 and 2.5, between 2.5 and 3, right? That gets you the 4. So if we work out these here, and just plug your numbers into the calculator, so 1 over 1 plus the square root of 1, that will give you a value of 0.5. Doing it with 1.5. Go with the 3 decimal places that the answer is going to be in. To be clear, you can give at this stage more decimal places if you want, and it could well be that in the examples where a question gives you a semi-complete table to begin with, that they'll give those answers in more decimal places needed. But yeah, for now, I'll just say, so that will be 0.674. For 2, that's going to get you 0.828. 2.5 is going to get you 0.969, and 3 is going to get you 1.098. Once you have those y values, we'll plug them into the formulas we had before. Once again, our h is going to be a half, so we'll have 0.5 over 2, and then our first y value was the 0.5. Our last one was the 1.098. Then add on to that 2 lots of each of the rest, so 0.674 plus 0.828 plus 0.969, and as I said last time, ideally you will be trying to keep as precise a values as possible in your calculator for doing this, but either way, this should then give you an approximate area for what's between that curve, the axis, and the lines 1 and 3, of 1.635 to 3 decimal places. Now that we have this, we can then compare to what the other part was, which was the definite integral between 3 and 1, which is basically the exact same as saying it'll be between the lines 1 and 3, of 5x over 1 plus the square root of x. Well, again, the only difference between this fraction and the previous one is the fact that it was times by 5. So it's 5 times greater. So just imagine you've done the integration as you just have. You would get this value here. So now we'll just do 5 times the 1.635, and that's going to get you an approximate area for this one of 8.175. Now, if we're all right with that, if that's all good, we understand how we're going to apply the formula, let's just go on to a question here. So you're given the curve y equals 8 minus 2 to the power of x minus 1, where x is between 0 and 4. Now complete the table below with the value of y corresponding to x equals 1. As we can see, most of this table has actually already been filled in for us. We just have to do 8 minus, and then 2 to the power of 1 minus 1, well 1 minus 1 is 0, 2 to the power of 0 is just 1, anything to the power of 0 is 1, so 8 minus 1 is going to give you a value here of 7. Next, we need to use the trapezium rule with all the values of y in the completed table to find an approximate value of the definite integral between 4 and 0 of 8 minus 2 to the power of x minus 1 dx? Well, because we used the trapezium formula from before, the difference here is 1. Our h is 1, that's what we're going up in. So 1 over 2. Our first y value is the 7.5. Our last y value is the 0. And we'll add 2 lots of everything else. So 2 add 7, add 6, add 4. And just putting that in your calculator, that gets you an approximate area of 20.75. Once we have that, we're then shown this diagram here, where figure 1 is showing a sketch of that curve that we've just been working with, the 8 minus 2 to the power of x minus 1, between 0 and 4. The curve C meets the x-axis at point A and meets the y-axis at point B. The region R, shown in the shaded figure 1, is bound by the curve and the straight line through A and B. Use your answer to part B to find the approximate value for the area of R. So now, not only are we working out the areas beneath curves and maybe some vertical lines on the axes, we've got some slanted lines. So this is more like a traditional, you need to find the shaded area between a couple of shapes that are overlapping with each other question. Well, we already know that this 20.75, that's going to be this entire area under the curve here, between 0 and this A, therefore is going to be 4. And we might as well label the other one as well. B, this is going to be the y coordinate when x is 0, so B is going to be 7.5. If you just want to be left with the shaded region for R, what we can do is take the whole area under this curve and take away this triangle from it. Well, for a triangle, you're using the formula of half base times height. So a half times a base of 4 times a height of 7.5. That's going to give you an area of 15. So, to wrap up with, if we'll just have our 20.75 minus that triangle of 15, that leaves you with just this bit above the triangle and then below the curve of 5.75 in area.